Okay. Now we have learned how we can prove that whether the limit of function of two variables doesn't exist. Okay. So yeah, we review a little bit. So this is uh, the definitions and precise definitions that if we have a surface, okay, for example here, this is a surface, and we are going to define its domain, okay, its domain, uh, and we define as a small circle. We call the domain delta, in which we are going to have all points that is available to approach the point AB inside this D delta. Okay, so we have this point here in the middle, and we can approach the delta, we can approach the point AB from many points inside this domain delta. Okay, so we can provide that that the delta can be in between of this circle. Okay, now by doing so, we can imagine if we have a limit, then our limit can be approached. Okay, so we can approach a point AB from any possible path. So we have several paths that is possible, and if we want to use that to approach, then perhaps the best way to approach is, for example, here we have point AB. So perhaps the best way is to let a line, maybe line here that is x equal a, or another line that is probably here, that is y equal b. Okay, so we can approach the point AB, and if you let x equal a or y equal b, then we can make out uh, our limit results. Okay, so we can have one variable as a constant. Okay, for example here, when we have x, y approaching 0, 0, then we can take x equals 0 and then approaching the limit to the equation of y, and then y equals 0. So by comparing these two, we know that when we have y equals 0, this is y equals 0, we have the result is 1. Okay, and when we have x equals 0, we have negative 1. So because from these two we have two different results, okay, then we call this is doesn't exist. Okay, so the limit will be exist if from every angle, from every perspective, from every path we can choose, the result should be the same, and we can say that the limit exists. Okay, that's the definition. And if we look on how the if we look on how the graph of our function is, you see that there is some notions in the origin, this part. Okay. You will see that it has it's bounced back. There is some ridge around the origin that correspond to the fact that it will it will be equal. So the function will be equal to 1 over 2, except at 0, 0, or at the origin. So if we look on, so at y equal x should be equal to half if we let y equal x. Oh, sorry. This is different functions. This should be limit. Yeah, this is a different function. Okay, maybe we can look here first. When y is 0, then we can check the limit. This will be 0. When x is 0, this is 0. Now you might think that it's equal and maybe it exists. Now my suggestions, there are another another equation that we can take. Okay, that is y equal x, that we can approach also. So we are going to have x or y. Let's become y or yeah, y. So we have y squared and then 2y squared. So it's half. Now if we look at the y equal x from this graph, y equal x will be around here. That this will be the y equal x, and you'll see that at 0 0 it's become undefined at 0 0. So it doesn't exist. So still we say that from this conclusions, this limit is also doesn't exist. So we can check through the line, okay, the line equations. Okay, the intercept y equals 0, x equals 0, or the y equal x that we can observe. And sometimes when you find a limit, you can check first. Okay, so to solve limit in two variables, first you might just checking the direct substitutions. We can also check the squeeze theorem. And we can check a different path or curve. I think for direct substitution and the curve, it will be, I think, easy to analyze. So let me go through an example. Okay, to show that whether this limit exists or not. If we check with different line, like for example x equals 0, y equals 0, or y equals x, it seems that it will be a 0, right? It will be a 0. It seems that it goes to be 0 from all this line. So we need to think with with another parameter or another curve that we can make up to. We can also check using the parabola x squared and y squared. And it also turns out to be 0 if we check. Now, if we use the precise definitions, let me copy this. Sorry. Let me copy, put here. Now, let the epsilon be a positive number and delta also positive. If let's say we have this as in definition, the distance formula, then okay, we are suspecting that it's 0 from our preliminary result. Okay, so we check through here. That is, we can take the square root for both implications here. Oh, sorry, it's the delta. Okay. And x squared will be less equal x squared plus y squared. Okay, it's because it's a positive number. And then since or maybe right, this is true because y squared is positive number, and we also see that this will be less equal 1, okay, as an implications. So therefore we'll have the this should be less equal 3y. Okay. Or we can write y in terms of the y squared, square root of y squared. And these terms, we know that this is less equal than x squared plus y squared. Okay. Now we choose delta equal epsilon over 3. Okay, because I think it's an obvious choice because it's having a 3 here. So we choose epsilon over 3 and let this square root of x squared plus y squared less than delta. Then we have we put back our original equation. It's simply similar what we have done in calculus 1 when we have the precise definition of limit. You can write that this is less than 3 delta, and this will be equal to 3 epsilon divided by 3 is equal to epsilon, and we will go back to prove that it's actually we are getting the same same answer. And then as a result, we can write as a conclusions by definitions, then this equal to 0. Okay, this is the first solution. Okay. Okay, let me wait for a few minutes and give you time to take notes. I hope you get the idea on this point here. This is basically using the precise definition of limit. Although actually, if you look on some of the line equations that we are applying, and also some parabola equations that we are applying, it seems that it will go to 0 in the result. But to make it more concise and true for all conditions, with the precise definition limit, we are see that it's proven to be correct. Okay, another solution that we can make, as I mentioned, we can have direct substitutions uh, using some different path or curve, checking one by one, and then checking through the squeeze theorem. Squeeze theorem. Maybe let me make it a little bit smaller. This part, let me resize. Okay, now if we look at from what we have from here, from this example here, we know that we can make, because the only way that this equation can be negative is because only of from the y, right? If the other part is quadratic, and we know that this is less equal than this 3y, right? 3y. So we can write this is less 3 absolute value 1. Now from this inequality, we can write the inequality as this, and this is, we are going to use this squeeze theorem. Let me make it a little bit smaller. Okay. Now as going 0, so y is going 0, and limit this is also 0, and the limit for the positive one also going to be 0. And by squeeze theorem, we say that the limit as xy going to 0, 0 is equal to 0. I think the squeeze theorem here showing you that when you have clear inequality, this part, I think it's easy to be in logically speaking, it's easy to be analyzed, right? The squeeze theorem. Okay. Okay, if you have any questions, maybe if you want to ask, you can write in the chat box if you want to ask questions. Okay. Any questions so far? I think good, right? Okay, now the next discussions. This will be about the continuity. So every part in calculus, usually it will defined in terms of derivative and integrations, and to define the whether the function is we can derive or not, the first thing we need to do is to check the continuity. I think better to just write the definition first, okay, for a function of two variables. Or maybe let me just review a little bit for calculus 1. Continuity means the limit exists as L, and the limit is equal with the function at that point. Okay, that means it's continuous. Now in function of two variable, is continuous at certain point AB if is equal with AB. I think it's a similar approach with the calculus 1. And then if we say that f is continuous on its domain if f continuous at every point AB in domain. Okay, so for example, if we look back the limit before, we have the function x squared minus y squared, x squared plus y squared. We have this function here. Now we know that this limit is doesn't exist, right? The limit doesn't exist for this function. So if you want to know whether it's continuous or not, then first we let the piecewise function, so let maybe h x y Okay, we have these two equations. Okay, if we let this piecewise h, this h is defined at 0, 0. Okay, just we write in the equations. But since h discontinuous because limit doesn't exist, then functions is discontinuous. Okay. But of course, if you just look at the function here, you check the limit doesn't exist, you can definitely say it doesn't exist. But if this is just to show you that whenever you find any piecewise functions like this, you need to check whether the limit is exists or not. Even though we let this two definition comes up in piecewise, still it doesn't. The limit doesn't. Okay. Okay. I think not really any additional explanations. It's just similar with the calculus one. Okay. Okay, let me continue. Okay, or maybe if you want to take notes. And I think my suggestions for our course, aside from having some practices, when we deal with some note taking in class, I think it's best to write some points that is essentials first. No need to write all things into your notes. Write the essentials, and then after finishing the class, maybe you can check which part that maybe you need to complete your notes, and you can watch the video, and you can skip some parts and going through which part that you need most. That and that's my suggestions. If you are trying to take all notes into so all notes from the class into your note, um, it takes time sometimes. So my suggestion, take some essentials only and review and complete later. Complete your notes later. Okay. We continue the next sections. Now we have 3 or more variables. And we say if it's 3, let's say it's going to approach ABC equal L. Now we can write in terms of epsilon delta definitions. if the point is in domain of the function, and the distance, we are going to use distance formula to write on the delta. So we have a small distance epsilon, and the function f continues at the point ABC if limit is equal to its point on the function. So generally speaking, when you have more than 2 or 3, 4, 5, 6, we can develop some general definitions. Okay? So we can write the general definitions as, so if f defined on a subset of domain at some space with many dimensions. Let's just say the dimension is n. It's not 2 dimensions, 3 dimensions. It's more than that probably. We can write the limit as, let me write a new notations to define it can be any n. It can be any number or any axis that can have into the equation. So let me write with bold x like this, and approaching bold a like this. It's not one point. It means that it can be more than 3, more than 4. Okay. This is equal L. This means for every number that has a positive epsilon, there will be positive delta such that if the x, the variable x, not on x, it can be xy, xyz, w, okay, and the distance if n is 1, then x is just x, a is just a. If n equal 2, then x will be x, y. Yeah, it's a factor. It's a factor. And this a will be a, b. Okay. And the x x minus a, this will be and if n equals 3, x become x, y, z, and a become a, b, c, and the distance and actually maybe to make it more clear, you can write the terms in terms of a factor like this. I think it's easy to write in notes. And the continuity we can write when we have limit and this is its continuity in more general terms. Okay, so that's 14.2, the limit of a function of two or more variables. The next sections will be about partial derivatives, and I will try my best to connect all the things that we learned in from 14.1, 14.2, and then it's connecting to 14.3, which is a partial derivative. I believe some of you familiar with partials eventually. I think because I think some physics or some formulations they are using a partial formula. Okay, let me begin the partial derivatives. Okay, now to begin with, remember that we have, let me just write the previous limit problem. One way we apply this limit, one way we apply or when we evaluating whether it exists or not, is we are going to look at the 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 point that we are going to approach. Okay, first is maybe we think on the path, right? The path can be x equals 0, y equals 0, right? So when we have x equals 0, then we treat x as a constant and we treat y as a variable. When we have y equals 0, then we are treating that y as a constant and we treat the other one, the x, as our variable. So if we think this way, and we are going to have, like for example, the the more general formula that we have. Let's say this is f x y. Then we can write, we let only x that vary when y is equal b, right? When we are doing this, actually we are thinking that the function can be simplified into just one variable. The other one is constant, right? Now, if we let only x, then we have a new function, let's say functions g, that has variable of x, that is equal to f x b, okay? If you remember what we did with the limit, here we have f x0 and we have f0y, right? Now, if this g, if we can derive g, if g is differentiable, differentiable at a, okay, at a, then we say it is partial derivative of f with respect to x at a b, and we are going to write it as f and then using subscript x and then at a b. We say that this is the partial derivative of f with respect to x, or simply we can say partial x to simplify the pronoun change. And then we can write in general the partial derivative with respect to x is where gx is f of x b. It seems going circle, but in practice, in some examples, we are going to see that it's actually not that complicated, okay, as long as we have consistency. Now, by definitions, this g prime, if we use the definition from the calculus 1, the limit definition, then we are going to have okay. So the definition for partial x you will see that the y is constant. We are only having a plus h, which means only x that has variable. And similarly, we say partial y we are going to let the x equal to a constant and y will be the variable. So this is partial derivative of f with respect to x at a b. The other one, let me make a copy. Respect to y at a b. So limit definitions finish. Now the notations for partial, you can choose which notations. You can write the partial x like that, or having the Leibniz notations like this one, or to be complete, we can write with x, y like that, or sometimes we can write z, okay, because ideally z is actually a function of x, y. And we can write also with d like that, x, f. I think it should be depends on your preference. Okay, any questions so far? Okay. Okay, maybe we can have some example. Let me just show you how to operate the partial. Okay. Okay. Now we need to find the partial x and partial y in those points 2, 1. So how to find partial x? Basically, partial x, we are treat y as a constant, and we are going to differentiate with respect to x. And partial y, we differentiate with respect to y, and x we treat as a constant. So first, we are going to look at the partial x. Now this will be 3x squared plus y as a constant. We differentiate to x, so 2x, and y cubed. And the other y, the last y, will be 0. Okay. Now partial y, x cubed will be 0, and the middle part will be 3 x squared y squared, and then minus 4y. Okay, and then we need to apply this 2 and 1. So we are going to have 12 plus 4, 16. This part will be 12 plus or minus 4, 8. Okay. Now another example, we give you more. Okay, let me give you this and evaluate f partial x, partial y. And I think I will give you a couple minutes to try it by yourself, and I hope you're trying to check by yourself, uh, doing some calculations. Okay, if you're done, you can write the answer partial x. Anyone calculate? You can write in the chat. What is the partial x at 1 and ln2? Can we find? Then 2, it's for partial x. I think not really correct. You need to, I think, having plus, right? Having plus because of the product rule for partial x. Any other answer? Almost correct. I found almost correct. need to check the squared. Yeah, almost correct, I found it. 2 plus the ln2 missing something. Yeah. But how we get the e squared? I think it should be just 4 ln2 plus 2. Let me just write the answer. I think for the partial x, we have the product rule for this two. Ah, Palis. Yeah. Yeah, you can check. Yeah. Correct, Eric. Correct. Okay, so this will be taking the product rule, the first one, this, and then plus x multiplied with the 2x, so 2x, and then multiply with x squared, y, e, and x squared, y. Okay. If you look at the point, you're going to have e, ln2, which is 2, right? And then plus 2 ln2 e ln2. So this will be 2 plus this will be 2. So we will have, let me just write 4 ln2, right? Okay. Okay. Now the second one, the partial y, yeah, it's just 2. Yeah, correct, Rian. So we can write we just differentiate e, right? So we'll have the x cubed e x squared y, and we have at the 1 ln2, this will be equal to e with ln2 or 3. Okay, I think we can move on to the other section, which is the geometric interpretations. Geometric interpretations of the partial derivative. Okay. Now recall that z is function of xy, and this will represent a surface, as we mentioned, I think in the previous discussion. And if the point at point AB, if this is related to C, then we can pinpoint A, B, C into our surface. And if you look at, let me check our graph, the curve. This will be the curve. Okay. So we will have this point P at the surface, especially when we are having AB, we are going to have this point, and then we will have, and if you imagine this as in the limit when we approach the point, when we approach the point, and then we have some different path, right? We have different path, and then from those limit, we are deriving how we define the partial derivative. Now, the partial derivatives at this point P, this will be our slope. This will be our slope. So let me write all the notions here. So P is lies on S, and if y equal B, so we will restrict observation only to the curve 1, and if x equal A, the observation only to the curve 2. Curve 1 and curve 2 both passing point P. Okay. And C1, we can write the functions as we defined previously, g of x. So this is where y is a constant b, and we write the terminology for the slope or a tangent is our first derivative at A, or we can write this as partial x AB. At C2, we are going to have the constant will be x and the variable will be y. We write as T2 or partial y AB. So, as a conclusion, the partial x and partial y can be interpreted geometrically as the slopes of tangent lines at P to trace C1 and C2 of surface S in planes y equal B and x equal A. So the plane means when we have in x, for example, here we have plane like this, right? And this will be showing that the curve, the C2 is on x equal A, and C1 is on y equal B. Okay, I hope you can see clearly from this plane right over there. Okay. So if you're asking to find a slope for a function of two variables, you'll have at least the partial x and partial y, because a function of two variables. And you will notice that you will have some certain definitions, because basically, because partial x means that it's it's dou z over dou x, you will see that you will, so z will change if x also change for some unit. Okay, let me give you the example to get a better understanding on what does the partial derivatives means in geometric perspective. Find slope in xy direction at half 1 for I think this is simple functions, not too difficult to be derived. We get the partial x from those functions is minus x, and partial y is minus 2y, of course, right? Now partial x at the point half and 1 is just negative 1 over 2, and partial y is negative 2. Oh, this should be at the half 1. Okay. Now what the result implies to this negative 1 over 2, because this is dou z over dou x, means that because it has negative, means that z decrease 1 unit for every 2 units increase in x. Okay. For this one, z decrease 1 unit for every 1 unit increase in y. Well, if both positive, then z increase, but since it's negative, z decreasing. Okay, I hope clear for this wording. Okay, now compare with the calculus one. We have the tangent, just a function of x, and f prime x will be the tangent, the slope, and through that slope we can find the linear equations, the tangent line equations, right? In our case here, we are going to find two tangent through partial x and partial y, and instead of finding line equations, we're going to find plane equation. Later we will discuss more on to plane. For now, let's discuss on some techniques first in partial derivatives that perhaps will be needed, and you will be also it will also help you to navigate the calculus course, and I hope it will be also useful in the future. Okay. Okay, I think we can move on, right? Okay. Now let's move to. Let me give you function of 3 variables. And let me give you the functions as an example. Fine. Okay. Now, how to deal with this question? We have a functions, or we have an equations that has 1, 2, 3 variables. And we need to find these two. In calculus 1, let me give you a context to understand this message. If in calculus 1, remember that we have, for example, if we have x squared plus 3xy plus y cubed, that's equals 0. If you want to find dy over dx, we are going to implicitly derive. Okay, so this will be 2x. So we are going to treat like an x, but we are treating y as function of x. Okay, and this will be having a product rule. So 3y plus 3x dy over dx and plus 3y squared dy over dx. And by doing some groupings, you will get the dy over dx, right? And then you can write in the answer. Now, for this part, we are going to use the same implicit differentiation, but now we are going to have three variables. So if we have this dou z over dx, dou x, means we are going to derive with respect to x and z defined as a function of x. Okay, now let me write the equations one more time here. And y as a constant. So for x, it's as usual, right? Okay, so x is as usual. For y, it's a constant, 0. For z, it's a function of x, so we will have 3z squared and dou z over dou x. And the xyz, this is a variable, this is a variable, this is a constant. So first we are going to have the product rule. Product rule 6 yz plus 6 x y, and then dou z dou x equal to 0. Let me simplify, become 2 and 2. So dou z dou x z squared plus xy. So 2xy. That's dou z over dou x. Now similarly, we are going to have same approach when we are dealing with y. So we treat x as a constant, and we treat y as a useful variable. So y, 3y squared plus 3 z squared, and now we are writing with respect to y, like that. So plus 6 xz plus 6 xy to z over y equals 0. I think this is similar. We will have similar equations. Oh, this is 2. Sorry. This is 2 also. So we can also using the implicit technique to solve the partial derivatives problem. Okay. Any questions? And I think I can continue. Maybe wait for you if you want to take notes from here. Okay, next is a function of more than variables, more than 2 variables. So it can be 3, 4, and more. If we have partial x at 3 variables x, y, z, we can develop our limit definitions as we mentioned before. This will be x plus h, and the other will be a constant. Okay, and similarly with other, you can also approach partial y, partial z. Now, if we can write in more general definitions, if we can write u as a function of n variables, so n can be any number, it can be 2, 3, 4, okay? And u is function of x1, x2, x3 until some xn to denote that how many variables it is. Then the partial derivative sum with respect to xi, I depends on the integer. This will depends on f, x1, xi minus 1, xi plus h, xi plus h should be here, and then xi plus 1, xn, x1, xi, xn. Okay. And we can write down the notations as or simply partial x or di. So actually, when you have equations that has more than one variables, and you want to do the partial derivative, you can do with many variables. So from these definitions, what the implication is, you can apply this for every function that has more than two variables, because it can be applied in general. Okay. Now if we have f, we want to find partial x, then we are going to derive with respect to x. Okay. So we are going to derive the e with power of xy, only that. The other will be a constant. So we'll have y, e, x, y, ln z. So if we have partial y, the same, it will be x. Now, if we have partial z, then this will be, we are treating ln z as our variables. So we are going to have e and over z. Okay, and if you increase the variables, it will stay, the technique still the same, and you can partially derive. Okay. Okay, now we are taking to next part, which is the higher derivatives. So what we did before is we are taking just partially one time, one derivative. So if we take 2 times, 3 times, 4 times to derive. Okay? For example, if we have partial x, okay, we already get partial x. If we try to derive one more, okay, we can also simply write this as x and x, like that. Or this is simply derivative with respect to x of our partial x. Or we can write in more clear that this will be the second derivative. Or we can write in terms of z. And similarly, we can write for the fyx, fxy, and fyy. We can write similar approach from there. So this we call second partial derivative. to give you more context on how we apply this higher derivative or second partial derivative, let me go through the f of xy, for example. Okay. Now let's just write, the question is finding the second partial derivative. So all the possibility that we are going to find. So first we write the partial x and partial y. So partial x, we will have 3y squared and then plus 10x y squared, right? And then partial y, we write down 6xy and then minus 2 plus 10x squared, x squared y. Now from this partial x, we can have partial x. So we are going to derive one more time with respect to x. This will turns out to be 20 or not 20, sorry, it's just x, so it should be just 10. So 10 y squared. If we have x y, means that we are going to have derivative with respect to y, so 6y plus 20x y. Okay, and partial yy is supposed to be 6x plus 10x squared. Okay, and the partial yx, this will be 6y plus 20x y. Okay, now you notice that this part is the same as this part. It has the same result, right? And this is, we are going to take into our theorem. We call this is the Clairaut theorem. The simple words for this theorem is just saying that the partial xy is equal partial yx. So no matter where you are start, if you are having same pattern, the partial pattern, no matter how you are going to reverse the order, you are going to switch the terms, as long as the number of the partial derivatives the same, it should be the same result. So if f is a function such that the partial xy and partial yx are continuous on open this R, then every point in real number will be now this is also implies that if you have three variables, for example, or if you want to take the third derivative, for example, x, y, x, this should be equal to x, x, y, or equal to y, x, x. Or if you have three variables, you have xzz, should be z xz also for ZZX. For any possibility, so you can switch the order of the reference, uh, the one that you are respecting to when you derive a function. And then in this partial derivative, we also can write in terms of a partial differentials. If, for instance, we can write this, we call the Laplace. You'll learn later on. I think in engineering of mathematics, the Laplace equations. We are not going to really into this for this partial differential. We will learn maybe later. Okay, any questions? Any questions? Okay, we can move on to the next sections, which is the tangent plane. I think just an intro for tangent plane. Okay. It's actually continuation from the conclusions of what we have in the partial derivative, especially the geometric, the shape, okay, what we are going to find. That will be the tangent plane. So the calculus 1, we find the tangent line. Calculus 2, we find the tangent plane. Okay. Okay. Okay, so 14.4, this is the tangent planes. Recall that calculus 1, we find the tangent line from the functions y equal function of x. In calculus 2, now we have a tangent plane, which is we are going to look at the surface of z that is function of two variables. As I mentioned, I think before, that we have two tangent lines, right? When we approaching the limit, and we define the limit definition in terms of derivative, which is equal to the tangent, the slope itself, and we can combine those two tangents into one plane. So those two lines are on the same plane, and those plane is the one that we call the tangent plane. If we draw, or if you see the graphs, this is what we are actually looking for. This is our objective. So we are going to find the tangent planes through the T1 and T2, these two tangents. So we can define this plane. Okay, so tangent plane to the surface. Let's say to the surface S. Okay, at point P is defined to be the plane that contains tangent lines T1 and T2. Okay, now we need to develop a more concise, more thorough equations for the plane. And I hope you still remember chapter 12, the equation of the plane. The equation of the plane let this point be as x0, y0, and z0. Now we have plane equation that is, we have the directions, right, a, b, c, and then x minus x0 plus b, y minus y0 plus c, c minus c0 equal to 0. Let's try to divide all by with c. So we'll have z minus c0, and I will move all through to the right side for a and b. So we'll have negative a over c, x minus x0 minus b over c, y minus y0. Okay. Now to simplify it, let the negative a over c becomes just a, small a, and negative b over c becomes b. So we have z minus z0, a, x minus x0 plus b, y minus y0. Okay. Now to simplify, what we are doing here is, if y equal y0, then at this certain plane, I have still remember the plane that we are talking before when we deal with the limit and the partial derivatives. This will equal to a x minus x0. So a is z minus z0 divided by x minus x0. In terms of how we can see this as a change, this will be our partial x, or our t1, or our rate of change of z with respect to x, right? Okay. And similarly, you will get, when x is equal x0, you will get that b is z minus c0 divided by y minus y0. This is partial y, or t2 is z over the y. Okay. So this a and b is actually partial x and partial y. Then we can make our conclusions for the plane equations. So suppose f, or the function, has continuous partial derivatives, then an equation of the tangent plane, the surface z equals f x y at p x0 y0 z0 is c minus c0 equal to partial x minus x0 plus partial y minus y0. Okay. So I hope you got the connection. You got the connection from the limit. When we deal the limit, we seems to take some different path. The path will be determined through the line that we are taking. For example, we take one variable as a constant, and then we can take the limit, and thus we also can take the derivative, okay, because the limit exists, the limit definition exists. And from those definitions, we simply look at the slope, and we have the two slopes that we can connect into a plane, a single plane. into plane equations. And the plane equation will be having partial x and partial y. Okay. And we can simply use the formula here to denote the tangent plane. Okay, any questions? If you don't have any questions, then I will stop until this tangent plane, and then we can continue next Monday. So if there's no questions, then we'll finish up until here. If you need the QR code, let me show you the QR code. Okay. So this is QR code. So if you haven't scanned, you can scan now. And if you have scanned, then you may leave the discussion, or if you have any questions, you still can chat with me, or maybe you want to ask something. I believe some of you suggesting to give the answer key for the midterm. I'm planning to, but some of you still not taking the exam because of some problems. So we need to wait until we finish all exam for all students. Okay, if you don't have any questions, then I will stop the class until this tangent plane. Okay. So yeah, you're welcome, Alice. Yeah. And see you Monday. Okay. Yeah, you're welcome, Eric. Carry on. Yeah, you're welcome.